Good morning to our lecturer. We are from Group 6, and today we are pleased to present our clinic appointment management system. Me, myself, Luzendo, joined by my teammates, Chan Yiwei, Ravi Abdul Adavia, and Kamis. So we will start off with database design and ERD.
Alright, my name is Chan Yiwei. Now I'm going to present about database design, which is the ERD. We use the cross-foot notations for this ERD. Now we look at the parents table, which is doctor and patients table. For the doctor table, we have the attributes such as doctor ID for the primary key and name, specializations, and phone number. And for the patients, we have the attributes patient ID as the primary key and name, IC number, gender, address, phone number, and email. And for the child table is appointment. The appointment ID is the primary key, appointment data time, appointment status, and the two foreign key is doctor ID and patient ID. And then if we look at the relationship between patients and appointment, one and only one patients may have zero or many appointments. So the use of one and only one appointment ensures that the appointment cannot exist without a valid patient. And the zero or many allows the patient's record exist even if the patient has no any appointments. And we look at the relationship between doctor and appointments. It is one and only one doctor may have zero or many appointments, which means a doctor may have zero, one or many appointments, but each appointment is designed to exactly one doctor. Okay, next.
Now moving on to relational schema and normalization. So from our ERD, we derive our relational schema. We map our entities into three distinct tables. First, the doctor table with attribute doctor ID as the primary key, and other attributes like doctor name, specialization, and phone number. Aside from doctor table, we also have the patient table, storing personal details like IC number, gender, address, phone number, email, patient's name, and also patient ID as the primary key. So the last table, the child table, we have the appointment table, which acts as our link, containing the appointment ID as the primary key, and appointment date, time, appointment status, doctor ID, and patient ID. So from the relational schema, we can't really see the data type or constraints for each attribute. So what we do is that we move them into data dictionary table. One of the example from our data dictionary table for appointment table. So as we can see from the table, we have data type for each variable, keys for each variable, and then constraint for each variable. Now we try to normalize our design into third normal form, 3NF. So how do we normalize it? So for 1NF, first normal form, all columns contain only single values. Next to the 2NF form, there are no partial dependencies. Every attribute depends on the entire primary key. So next, we have the 3 normal form, which is no transitive dependency, ensuring no non-key attributes rely only on the primary key. So as we can see from our table, all of these foreign key depends on the primary key. So which means that non-key attributes depends on only the primary key. So we can say that our design is in 3 normal form. Now we'll be moving on with the SQL DDL implementation. We'll first start off with creating the parents table. So to avoid any referring problems in our child table, which is a appointment table, we first start by creating parents table using the create table statement, and then listed all the attributes in corresponding table and their data types and constraint. Next, we will be assigning primary key according to their corresponding table. So for example, in patient table, we will stated that patient ID as the primary key. Next, we will be moving on with creating a child table. So again, we implement the create table statement to create a appointment table, and then listed all the attributes alongside their data types and constraint. Next, we apply foreign key statement stating that doctor ID and patient ID are the foreign key in this table, referencing to doctor ID in doctor table or patient ID in patient table. Next, we'll be moving on with DDL testing. So in DDL testing, we'll be violating a check constraint from appointment status. So to avoid any errors including referencing, since there are no records inserted in patient and doctor table yet. So we'll start by inserting a record in doctor and patient table. Next, we will try to insert a appointment record which violated the check constraint from appointment status. So as we can see, we inserted a Y value in the appointment status. And what's the result shows that since the check constraint only accept schedule, completed, or cancel, we have successfully violated the check constraint with a error ORA 02290. So now we'll be moving on with SQLDML testing.
Hello, Doctor. Now, let's move on to the practical heart of our database, which are data manipulation language or DML. This is where we bring the system to life by populating it with data and managing day-to-day operations. So we will demonstrate the four essentials using the CRUD, create, read, update, and delete. So first, let's look at create, where we insert a five valid record in each table. So this initial data population is crucial for testing. For example, this statement will add a new doctor to the system. We can see the successful insertion in the output, confirming the table structure and constraints are working correctly. Similar insertions were performed for patients and appointments, establishing the foundational relationships in our database. Next slide. For update statement, this update operation, a common real-world task is changing an appointment status, for instance, from scheduled to complete after a patient visit. Here is the SQL update statement. It's precise. We target the appointment table and change the appointment status only for a specific patient ID. In this case, P1002. The slides show the state before and after the update. You can see the targeted record status successfully changed to complete, while all other records remain untouched. This demonstrates how we can modify specific data without affecting the integrity of the rest of the database using the update set and where. Next slide. For the delete statement, we have the delete operation. There are times when an appointment needs to be cancelled and removed from the system entirely. This delete statement removes a specific appointment by its appointment underscore ID, which is A1002. The output here is key. After the deletion, we run a select query on the appointment table. The result set shows that the record with ID2 corresponding to A1002 is now gone. The remaining records are intact and the IDs are still in sequence, showing a clean deletion. This also tests our foreign key constraints to ensure associated data is handled appropriately, maintaining referential integrity.
All right, I introduce myself again. My name is Chani Wei. Now I'm continue the presentations for SQL query testing. All right, the first one is display all the appointment with patients and doctor name. It's because of foreign key in child table, which is appointment, is only store the values such as patient's ID and doctor ID from the parents table. So we use the join statement to allow the parent tables can be linked to the child table, which is appointment, to enabling all the attributes from the parents table can be retrieved. So we look at the output is already list out all the appointments with the patient name and doctor name. Yeah, next. All right, the second one is list appointments for a specific doctor. The select statement is to select all the appointments records, and where statement can be filtered out a specific doctor with ID D1001. So this confirms that the system can be filter appointments based on the doctor identity. So if we look at the output, we already list out all the appointments that assigned to the doctor with ID D1001. Okay, next. Okay, the third one is count total appointments per doctor. The doctor D and appointment A is the table alias for easier reference, and the count is for us to count the number of appointments associated with each doctor. And S renames the output column, and left join can list out all the doctors, even the doctor have no appointments at all. And we also group by the doctor name. So we look at the output, we can see that all the appointments total is list out grouped by the doctor name. So this query test is test the system able to perform the aggregations of operations across related tables. Next. All right, the next one is search patient record. We use the like percentage, multi-percentage symbols to perform a partial match search. So the percentage symbol is represent any number of characters before or after the word multi. So it can allows us to more flexible to search even if the full patient's name is unknown. So this test can confirm that the database can support efficient records retrieval without requiring the exact matches. So if we look at the output, we already find out the patient's name multi and the patient's details. All right, next one. And the last one is sorted list of appointments. We use the select to select all the rows of the appointments. And the order by can sort them into the chronological, which is temporal order based on the appointment dates and time. So this query tests the system able to sort data So this query test can able to sort the data accurately based on the time, which is very crucial for the appointment scheduling. All right, next.
So after verifying our DDL and DML operations, we now move on with transaction and data integrity testing. So first, we start by testing the rollback statement. We initiated a transaction block where we inserted a appointment value with appointment ID equals to A1007. Then, however, instead of committing this transaction, we immediately issue a rollback command. As you can see from the output, when we subsequently try to select that record, the result was no row selected. This confirms that the system successfully undo the temporary changes, proving that we can safely revert operations if an error occurs before a commit. Next, we tested the commit command. We start by perform a similar insertion for a valid appointment with appointment ID equals to A1007 alongside all the details. But this times we follow it with a commit statement. The output shows that the record was successfully retrieved afterwards. This verified that our system can securely and permanently persist the data into hard drive once a transaction is finalized. So meaning that even if you close your SQL program, you can still retrieve this A1007 successfully. Next, we'll be moving on with transaction interruption. Finally, we tested how the system handles interruptions and error during the transaction. So in this scenario, we successfully inserted and committed a valid record A1007. Then we immediately attempt to insert a second invalid record A1008 where the appointment status carry a value of Y. As expected, the system triggered a check constraint violation and crashed script for that second entry. So in this scenario, the transaction should be rolled back, including the first insertion should be sorry, 重新来过. So finally, we tested how the system handles the interruptions and error. In this scenario, we successfully inserted a valid record with appointment ID equals to A1007. Then we inserted a second invalid records with appointment ID equals to A1008. And what is invalid is that in the appointment status, we inserted an unexpected value Y, which is not scheduled, cancelled, or completed. So as expected, the systems trigger a check constraint violation and crash the script for the second entry. However, because we had already issued a commit statement for the first insertion, the first record A1007 was saved into the hard drive permanently. So this demonstrates that our constraint effectively block bad data while our transaction controls ensure valid data remain constrained persistent. So now we move to the conclusion. So in conclusion, our group successfully developed a functional clinic appointment management system. So we start by identifying our key entities, patient, doctor, and appointment. Then we represent them in a entity and relationship diagram, ERD. Next, we converted this ERD into a relational schema and normalize it into third normal form 3NF to prevent data issues. Next, we perform the SQL data definition language DDL statement to ensure data validity with constraints like primary key and foreign key. Testing confirmed that the database correctly handles invalid inputs and supports essential CRUD operations. Then, transaction control statements were used to maintain data consistency, demonstrating rollback mechanism for failed transactions. This system effectively manages clinic appointments and can be enhanced with additional features in the future. That's all from Group 6. Thank you. Your attention is much appreciated.